Look up at the night sky. Every point of light you see is not just a star. It is a possibility of planets, oceans, atmospheres, chemistry, heat, darkness, and maybe life. For thousands of years, humanity has asked one question that refuses to disappear. Are we alone? But today, that question has changed. We are no longer asking it with mythology or imagination alone. We are asking it with telescopes, spacecraft, chemistry, biology, and machines moving across alien worlds. The search for life in outer space is no longer science fiction. It is one of the greatest scientific investigations in human history. And the answer may not come from a giant alien city, a radio message, or a flying saucer in the sky.
The first alien life we discover may be microscopic. It may be buried beneath Martian rock. It may be swimming in a dark ocean under the ice of Europa. It may be hiding inside the plumes of Enceladus. Or it may appear as a faint chemical fingerprint in the atmosphere of a planet orbiting another star.
This is the real search for life beyond Earth, and it may change everything. The only life we know. Before scientists can search for alien life, they must begin with the only example we have, Earth. Our planet is alive almost everywhere.
Life exists in boiling hydrothermal vents at the bottom of the ocean. It survives in acidic lakes, frozen deserts, volcanic rock, radioactive environments, and deep underground places where sunlight never reaches.
These organisms are called extremophiles, life forms that survive in conditions once thought impossible, and they changed astrobiology forever. If life on Earth can survive in darkness, pressure, radiation, freezing cold, boiling heat, and toxic chemistry, then maybe life elsewhere does not need a blue sky, green forests, or perfect Earth-like conditions.
Maybe life is tougher than we imagined. At its deepest level, life needs a few basic things. It needs chemistry, elements like carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. It needs energy from sunlight, chemical reactions, radiation, or heat from inside a planet. And most importantly, at least for life as we understand it, it needs liquid water. Water is not just an ingredient, it is a chemical stage. It allows molecules to move, react, combine, separate, and become more complex. On Earth, wherever scientists find liquid water, they often find life. That is why the search for alien life is also the search for places where water, chemistry, and energy come together.
The ocean worlds. Imagine a moon covered in ice. From space, it looks frozen, dead, silent. But beneath its cracked surface, there may be a global ocean, a hidden sea warmed not by sunlight, but by gravity. This is Europa, one of Jupiter's moons.
Europa is pulled and stretched by Jupiter's immense gravity. That gravitational flexing may create heat inside the moon, keeping an ocean liquid beneath its icy crust.
If that ocean touches a rocky seafloor, chemical reactions could occur there, similar to the hydrothermal vents on Earth, where entire ecosystems survive without sunlight. That makes Europa one of the most exciting places in the solar system, not because we know life is there, but because the ingredients may be there.
Water, chemistry, energy, time. NASA's Europa Clipper mission will investigate whether Europa has conditions that could support life. It will not land and scoop up alien creatures. It will fly close to Europa again and again, studying the ice, chemistry, magnetic field, and possible ocean beneath.
Its goal is not to prove life exists. Its goal is to ask a more careful question: could Europa support life? That is how real science works. It does not jump to the most dramatic conclusion. It builds evidence.
But Europa is not alone. Around Saturn, there is another icy moon called Enceladus. Enceladus is small, bright, and covered in ice. But near its south pole, giant cracks blast plumes of water vapor, ice grains, and organic molecules into space. A spacecraft does not even need to land there to sample material from the ocean. The moon is throwing pieces of its hidden sea into space. The Cassini spacecraft flew through these plumes and found evidence of water, salts, organic chemistry, and ingredients linked to habitability. Enceladus may have a subsurface ocean, chemical energy, and organic molecules, three key pieces in the puzzle of life. If life exists there, it would probably not look like anything from Hollywood. It might be microbial, simple, small, chemical.
But scientifically, that would be one of the greatest discoveries ever made, because finding even a single microbe beyond Earth would prove that life is not unique to our planet.
It would mean life can begin twice in one solar system. And if it can happen twice here, then across a galaxy of hundreds of billions of stars, it may happen almost everywhere.
Mars, the planet that may have been alive. Mars is different. Europa and Enceladus may hide oceans beneath ice, but Mars is a world that may have been habitable long ago. Today, Mars is cold, dry, and exposed to radiation. But ancient Mars was not always like this.
Billions of years ago, Mars had rivers, lakes, deltas, and perhaps a thicker atmosphere. Its rocks preserve chemical clues from a warmer, wetter past. That is why rovers like Curiosity and Perseverance are so important. They are not searching for little green creatures walking across the red sand. They are searching for signs of ancient microbial life, traces left behind in rocks, sediments, minerals, and chemistry. Perseverance is exploring Jezero Crater, a place that once held a lake and river delta. On Earth, deltas are excellent at preserving signs of life because they collect layers of sediment over time. If ancient microbes ever lived on Mars, rocks in places like Jezero may have trapped their chemical fingerprints. But this search is difficult. A strange rock pattern is not automatically life. A chemical signal is not automatically biology. A mineral shape may look biological, but form through non-living processes. That is why scientists use the term biosignature very carefully. A biosignature is evidence that may point to life, but it must be tested against other explanations. The universe can imitate biology. Chemistry can create patterns. Geology can create structures. Planets can produce gases that look suspicious. So the question is not only did we find something interesting, the question is, can anything else explain it? Science must be skeptical because the discovery would be too important to get wrong. The life we may never see directly now move beyond the solar system. For most of human history, we did not know whether planets around other stars were common. Now we know they are everywhere. Thousands of exoplanets have been confirmed, and many more candidates are waiting to be studied. Some are gas giants larger than Jupiter. Some are scorched worlds orbiting close to their stars. Some are frozen, dark, wandering planets. And some may be rocky worlds in the habitable zone, the region where temperatures could allow liquid water on the surface. But these planets are unimaginably far away. We cannot send a rover there. We cannot scoop up their oceans. We cannot drill into their rocks. So scientists search for life from a distance. They study light. When a planet passes in front of its star, a tiny amount of starlight filters through the planet's atmosphere. Different molecules absorb different colors of light. By studying that missing light, scientists can infer what gases may be present. This is called spectroscopy. It is one of the most powerful tools in the search for life. If a distant planet's atmosphere contained water vapor, carbon dioxide, methane, oxygen, or ozone in unusual combinations, scientists might ask whether life is involved. The strongest clue would not be one gas alone. It would be disequilibrium, a chemical imbalance, an atmosphere filled with gases that should react with each other and disappear, but remain present anyway. That could suggest something is constantly replenishing them. Maybe geology, maybe chemistry, maybe life. A living planet changes its air. Earth is the proof. From far away, Earth's atmosphere would look strange. Oxygen, methane, water vapor, and other signals coexist in ways that reveal a planet chemically active and biologically transformed. To an alien telescope, Earth would not just be a rock, it would be a clue. The Fermi paradox. But if life may be common, another question appears. Where is everybody? This is the Fermi paradox. The Milky Way is ancient. It contains hundreds of billions of stars. Many stars are older than the Sun.
If intelligent civilizations are common, some could have had millions or even billions of years to develop technology, spread, communicate, or leave evidence behind. And yet, the universe seems quiet. No confirmed signals, no confirmed alien artifacts, no undeniable proof of extraterrestrial intelligence.
There are many possible answers. Maybe life is common, but intelligent life is rare. Maybe microbes are everywhere, but civilizations almost never emerge. Maybe civilizations destroy themselves before they become interstellar. Maybe advanced life chooses not to broadcast.
Maybe space is simply too vast and we have barely begun to listen. Or maybe the signals are there, but we do not yet know how to recognize them. The silence of space does not prove we are alone. It proves only that the search is difficult.
Imagine standing beside an ocean at night, lowering a cup into the water, finding no fish inside it, and concluding the ocean is empty. That is where humanity is now. We have sampled only a tiny fraction of the cosmic ocean.
What would discovery mean? The discovery of life beyond Earth would divide human history into two eras, before we knew and after we knew. Even microbial life would be revolutionary. It would tell us that biology is not a miracle limited to Earth. It would mean the universe has a tendency to organize matter into living systems when conditions allow. It would transform biology, philosophy, religion, astronomy, and our understanding of ourselves. But it would also humble us. For centuries, humans believed Earth was the center of everything. Then we learned Earth orbits the Sun. Then we learned the Sun is one star among hundreds of billions in the Milky Way. Then we learned the Milky Way is one galaxy among billions. And now, perhaps we are approaching the next great shift. Life itself may not be centered on Earth. We may be one branch of a much larger cosmic story. The most likely first contact. When people imagine first contact, they imagine a message, a ship, a face, a voice from another world.
But the real first contact may be quieter. A molecule in a plume, a fossil-like pattern in Martian rock, an atmosphere out of balance around a distant exoplanet, a chemical signal that cannot be easily explained by geology alone.
It may arrive not as a dramatic announcement, but as a scientific debate, a paper, a measurement, a second observation, a third instrument, years of testing. The first evidence may be uncertain, then stronger, then impossible to ignore. That is how the universe may reveal life to us, not all at once, but piece by piece.
The search for life in outer space is not just a search for aliens. It is a search for our place in existence. It asks whether life is rare or common, whether Earth is an exception or an example, whether the universe is mostly dead matter or quietly alive in ways we have not yet imagined.
Maybe somewhere beneath alien ice, a dark ocean is moving. Maybe on a planet orbiting a red star, chemistry is becoming biology. Maybe light from a living world is already crossing space toward us, carrying the answer inside its spectrum. And maybe one day we will detect it. Not with fear, not with fantasy, but with evidence. The universe is vast. The silence is deep. But silence is not the same as emptiness. And somewhere out there, life may already be waiting to be found. This is infinite science, and the greatest discovery in human history may still be ahead.